Students, today we will have a look on one of the chapter of your third module, that is mean memory management. Myself Sunanda Beredar, handing over the lecture. So this is having different sections to be covered, such as background swapping, contiguous memory location, segment paging, structure of page table, and some examples of memory management for the different architectures. In this particular video, we are going to look into the background swapping and what is memory allocation. So in the next video lecture, we will be having looking into some problems. So this is a very basic need for learning those problems. So let us go to the background. So as you know that in order to execute any particular program, it must be brought into the main memory first. So main memory and registers are only storage CPU can access them directly. Memory read only sees a stream of addresses, reads the request or address in the data and write the request. This is the main task of memory read. It is not doing any processing, that rather it is able to observe a stream of addresses, and it can do a read or write request, and it can accordingly do reading or writing of the data. So registers access in CPU in one CPU clock or lesser than that. That is, they are faster to access than the main memory, whereas main memory can take many cycles, causing a stall, that is delay. So cache is lying in between these two, main memory and the CPU registers. So as you know that it is not possible to hold a bigger program in a register. We are obviously, as you know that every program, to make it as a process, in order to run it, it has to brought to the main memory, and protection of the memory is also required to ensure the correct operation of that particular process. So here we are looking into two main things, that is terminologies that we are coming across is base register and limit registers, which define the logical address space. So every CPU must check every memory access generated in user mode to ensure that that request is between the base and limit for that user only. So you can observe here we have a memory layout in this operating system is present, and many of the processes are present, and this is a blue one is a empty memory. So here you can observe if any user is running this particular process, second process, its base is, that is, it is starting at 340. Its address is starting at 340, and its address is ending at 4,20,940. So this process can access only these addresses, not beyond this. So beginning of this is indicated by base, and limit is telling how many bytes of memory it can access. You can observe limit value is 12,900. If we add it to the base value, you are going to get this 42,000, that is 4,20,940. So as I said in the first slide, that here protection of memory is required to ensure the correct operation. So this is how the hardware is going to protect the main memory access. So that what we call as a hardware address protection here. The CPU generated address, we call it as a logical address, right? So then this logical address is compared with the base address. So what comparison is done is logical address should be greater than the base address. So whatever is the particular address generated should be larger than the base, larger than or equal to base address. If it is so, then only it is going for the next stage. In the next stage, it is checking that it should be lesser than the base plus limit. If it is so, then only it is accessible. Otherwise, that address generated by the CPU is invalid, and that is what trapped to the operating system, indicating that it is an addressing error. It should lie between the base and base plus limit, right? That is if you look at this particular example, it should lie between 340 to 4,20,940. So base here is having the starting address, limit is the length of this whole address space accessible to that particular process. So it should be within this range, it should not be below this or above this range. So that is checked with the hardware associated with this. As you can observe by using the comparators, this is checked. If it is crossing any of these, then the error is reported. So let us look into a concept called as address binding. So program on disk, when it has to be brought into the memory, we should assign it should be loaded into the particular address. Usually logical address starts with 000. Further it address represented in different way at the different switches also. So source core addresses are usually symbolic. When it is compiled, the real address is bound to that particular address. So linker or loader will bind the relocatable addresses to the absolute addresses. Absolute address always begins with 00, and then the beginning of that process's address is added to that to get the relocatable addresses, and it is used by the linker and loader. So each binding maps to one of the address space into another. So binding of instructions and data, binding of addresses to instructions and data is happening at three different stages. One is at compile time, and one more is at load time, and another one is execution time. If memory location is known well in advance, absolute code can be generated, and you must recompile the code to start in order to implement location changes. Whereas load time is must be generated as a relocatable code. Memory location is not known at compile time, then it should be able to relocate at any time, because it is going to be known at load time only. Execution time, so the address is not binded till the runtime. If the process can be moved during its execution from one location to another, then it can be done at the execution time. So this requires the hardware support for address mapping, that is as we have seen, base and limit registers are required. Again we'll go through the different stages of a particular user program that undergoes in order to run. So initially we'll be having a source program. It is compiled or assembled. This we call as a compile time. An object module is generated out of this. So then it is sent to a linkage editor in order to assign the relocatable addresses to this. So then it is loaded onto a particular through the loader. It is loaded onto the main memory in binary form, as you can observe here. So this part, when memory is assigned to that, then we call it as a load time, and sometime it is postponed until to execution time. So if it is done at this time, we call it as a runtime address binding or execution time address binding. So even we know that some system library files are loaded statically, as well as they can be dynamically loaded during the execution time also. So what is logical address and what is physical address, and what is logical address space and physical address space, that we'll look into in this particular slide. Logical address is the one which is generated by the CPU. It is also called as a virtual address. Really it is not access available on the main memory. Physical address is the actual address seen by the memory unit. So logical and physical addresses are same in compile time, they are not changing, and at load time address binding schemes they are differing, and also in execution time address binding scheme is different. And logical address space is the set of all logical addresses generated by the program by the CPU, whereas physical address space is set of all physical addresses generated by a program again, and that is done by the those are seen by the memory unit. So one major difference that we are able to see is logical address is virtual address, whereas physical address is the actual address which is seen and referred by the memory unit. And all the set of such addresses, we call them as address space. If it is a set of logical addresses, we call it as a logical address space. If it is a set of all physical addresses, we call it as a physical address space. So we'll have a look on something called as a memory management unit, which is a hardware. At runtime it maps the virtual to physical address, that is, it is mapping the logical address to physical address again. So it is making use of a base register. It is now called as a relocation register. And how it works, how it converts the virtual address into real physical address, that we'll see here. So it is called as a dynamic relocation using a relocation register. Relocation register is nothing here other than the base register. It is base register only, as we have already seen in one of the previous diagrams. CPU generated address is a logical address, which is something like 346. This is added with the base register value or relocation register value. It gives you 14,346, which is the actual address on the memory. So dynamic linking and